Quasicrystals are a unique class of solid materials that exhibit long-range order without periodicity. This means that while their atomic structure is ordered and non-random, it does not repeat itself in a regular pattern as in traditional crystals. Discovered in 1982 by Dan Shechtman, who later received the Nobel Prize in Chemistry in 2011 for this groundbreaking work, quasicrystals defied the long-standing belief that all crystals must possess translational symmetry. Instead, quasicrystals often display symmetries that are forbidden in periodic crystals, such as 5-fold, 8-fold, or 10-fold rotational symmetry. Structurally, quasicrystals can be described mathematically through concepts like Penrose tiling or higher dimensional projections, which allow for the visualization of their non-periodic but ordered atomic arrangements. These materials are typically metallic alloys composed of elements like aluminum, copper, iron, or nickel, and they often form under rapid solidification or specialized synthesis conditions. One of the most well-known families of quasicrystalline materials is the LMNPD system, although many other systems such as Alcufe and TZRNi also exhibit quasicrystalline phases. Quasicrystals possess a number of remarkable physical and chemical properties that distinguish them from conventional metals and crystals. They tend to be extremely hard and brittle, have low thermal and electrical conductivity, and exhibit high resistance to corrosion and oxidation. Furthermore, their surfaces are often low in friction and non-stick, making them useful in certain industrial applications. From a scientific standpoint, the discovery of quasicrystals has deeply influenced the field of crystallography, leading to a broader definition of crystal structure and a reconsideration of symmetry principles in solid-state physics. In terms of industrial applications, quasicrystals are employed in a variety of niche uses due to their unusual surface and mechanical properties. For instance, they have been used as coatings on frying pans and other cookware for their non-stick properties, offering an alternative to Teflon. Their high hardness and wear resistance also make them suitable for use in surface coatings for cutting tools and machine parts. Quasicrystalline materials are also being investigated for use in hydrogen storage, photonic and phononic applications, and thermoelectric devices due to their low thermal conductivity and complex electronic structures. Additionally, some polymer-based composites have been reinforced with quasicrystalline particles to improve mechanical performance and thermal stability. On the scientific front, quasicrystals serve as an important model system for studying aperiodic order, electron localization, and phonon scattering. Their unusual diffraction patterns, which reveal sharp Bragg peaks without translational symmetry, have spurred extensive theoretical and experimental research in condensed matter physics and materials science. In particular, the study of quasicrystals has led to new insights into the nature of atomic bonding, phase transitions, and the thermodynamics of complex alloys. Recent discoveries of naturally occurring quasicrystals in meteorites have even sparked interest in cosmochemistry and the conditions of matter formation in the early solar system. Concrete examples of quasicrystalline materials include icosahedral Al-Mn alloys, decagonal Al-Nico quasicrystals, and dodecagonal ZnMgSc systems. The icosahedral Alcufe alloy is especially notable for being one of the first widely studied quasicrystals and is still commonly referenced in both theoretical and applied research. In addition, synthetic quasicrystals with tailored properties are continuously being developed through advanced techniques such as rapid solidification, sputtering, and atomic deposition. In summary, quasicrystals represent a fundamentally new way of understanding order in solid matter. Their unique structures, rare symmetries, and extraordinary physical properties have opened up a rich area of research that bridges crystallography, materials science, physics, and even cosmology. Although still limited in widespread industrial adoption, the continuing advancement of synthesis techniques and deepening scientific understanding are likely to expand the role of quasicrystals in future technological applications.